Hello, hello. My name is Joe Wingard. Today I'm going to talk to you about an application I've developed I call Service Engine. Before I do that, I'd like to draw your attention to the link at the bottom where you will be able to download the slides that I'm about to present. The URL is tinyurl.com/conf42-service-engine. Okay, Service Engine, what is it? In short, Service Engine is an application that you can run that will connect to many really popular databases, and it will auto-provision REST, GraphQL, and gRPC interfaces that support full CRUD to any of the tables, views, and materialized views inside of that database. That's what it is. The application is available in multiple ways. You can see this on the right side of this slide, where I have it listed as multiple implementations. This is a JavaScript conference, and I have built this framework and released it on NPM. So if you were to use npm I Service Engine, you would download my framework. So the number one there, service-engine, there's the repository that holds the source for the npm library. Number two, service-engine-docker. That holds a node application that implements the npm package and also serves as the source for the generic Docker image. Then there's a third implementation, service-engine-template. If you were to go there, you would see an implementation of the public generic Docker image. And this is what I use when I need to implement Service Engine myself. The key features of Service Engine are that it auto-provisions the resources. I'm going to go into detail into how this works in some of the following slides, but the fastest way to explain it is that it when the application starts up, it executes a survey, a database survey query, and it pulls internal tables, and it uses that material to hydrate the interfaces. Validation at the source. I've used Happy Joy for a long time as validators. I think Joy has moved to a different organization, but I've used Joy validators for a long time. And this application supports validating every call, reads and writes. This application also supports database schema migrations. Connects has terrific support for schema migrations, and I believe every feature provided by Connects is supported by the Docker image. There's some additional functionality that's fairly detailed and extensive. There's 2.5 hours of documentation on YouTube, 2.5 hours of video that I've put up, and there are links to those later in the deck. But an example of one such feature is there's a mechanism that allows you to intercept a query to the application after it's validated, but before it gets executed against the database. This would be useful. This was useful to me. An actual use case I had was appending a partition key to an inbound query that was blind to the user. So it optimized the query, and the user didn't know why. All right, moving on. How it works. The diagram, the image in the bottom left with the green database and the blue hexagon and the three horizontal bars. The database, this application supports all of the databases that are supported by Connects. That's postgres, including with the postgis extension, mysql, sqlite, Oracle, Redshift, and SQL Server. The way it works is that the application connects to the database. It surveys all of the tables, views, and materialized views. It collects names of all the fields. It determines whether or not a null value is acceptable. It determines whether each field is part of a primary or unique key, and it uses that information to build Happy Joy validators, which is annotated above and on number 3. After it builds validators for each database resource, it provisions REST, GraphQL, and gRPC services that allow reading and writing to the different resources in the database. I'm going to go into detail on the next slide into the REST interface. I'm not going to spend any time going over the GraphQL and gRPC implementations. Just know that they're going to be very similar to the REST interfaces abstractly with the different components that are supported. If you want to see how the GraphQL and gRPC implementations are done, you can either check out the source code and service engine, or you can check out the 2.5 hours of YouTube video. Well, on the right here, in those cards marked 2 and 3, I have basically the minimum that's required for you to run this application via public Docker image, and give it a whirl. So if you're using a database that's supported by Connects right now, there are a couple considerations which I'll hit at the very end, but generally speaking, if you're running one of the supported database dialects, you should be able to build a .env file as indicated in CRUD2, and then execute the command line Docker command on line 3, and the application will be running. I'm pretty verbose with my logging statements, so you should know right away, and it should give you some links you should be able to click on. Some of the links that are available are just very general. There's a general health check route. So now I'm on the bottom right of this slide, marked with the number 4. There's a health check route that lets you know the application's up. Then there is an open API route that auto-generates the Open API 3 document, which is really useful for either rendering the Open API 3 documentation in a web application, kind of like the Swagger user interface, or you can also use that endpoint to import the API documentation into API clients like Insomnia or Postman. The next endpoint is the .proto file. This is the file that's needed to make gRPC calls. So you would be able to hit that endpoint, download the file as text, and use it in a client to make the gRPC calls. The final link, this service only gets provisioned if the node environment passed to the application is not production, but it's a GraphQL playground. Moving on. Oh, what did I miss? Yeah. Key concepts. So earlier I said when you run the application, it starts a REST service on port 8080 and a GraphQL service on port 8080 and a gRPC service on 5051. So here I'm going to go into how the REST interface works. The other interfaces operate in similar manners, but you would have to take a look at them. What you want to do is you want to get an idea for the general pattern, because the pattern is what's defined, and that gets hydrated by the results of the database survey. So at the top here, the key concept, service call to structured query language. That's the exercise, right? You want to turn an HTTP call, a REST call, into a SQL statement, and then you want to execute it. So you want to go from card 1 to card 2. Card 1, most of that URL I will explain later. The sample app name, that's a configuration variable you pass into the application. Dash service, that has meaning, that I'll hit on the next slide. But the final part of that path, schema underscore table. The majority of the databases that are supported by Connects support the schema object. So you have a database, then a schema, and that schema holds tables, views, and materialized views. SQLite being the outlier there. SQLite, to my knowledge, doesn't support schemas. However, this is the general structure for how you would call a specific resource inside of your database. Then the next three, the query string arguments that follow, occupation, state.in, and handle.like. These are fields on the object, followed by, there's dot notation, then what follows the dot is the SQL operator you want to employ. So occupation has no dot, there's no operator defined, so it's going to fall back on the default, which is equal. State.in, it's using the in operator, and the value that's passed there, so it's occupation engineer, state, and New Jersey or Pennsylvania. That's how you would read that. And then handle is using the like operator, and I'm passing it sudo percentage sign. All of the operators that are supported are marked in table 5, which is on the top right. And so you have support for the logical operators. You have support for not or like, null and not null, and not in. You have support for range. And then if you're and not range. If you're using PostgIS and the database resource has fields that are of geometry types, those specific fields you will also get access to 3 geo functions, geo operators, geometry operators. Right now what's supported is bounding box queries and radius, where you put in the lat and long of the center point and then the number of meters that you want to search, and also a custom polygon. And the value for custom polygon would be a WKT string, a well-known text string. Looking at that table on number 5, I have the field operator, and it maps to the SQL operator. And then there's 2 other columns, multiple supported arguments and number. So multiple supported arguments is whether or not you can submit multiple values separated by default by commas. So in the example there, I have state.in, New Jersey, Pennsylvania. New Jersey, pipe, Pennsylvania. The pipe is being specified as a separator at the bottom of that list. I'm aware of the typo. I noticed it earlier today for the first time. But by default, if you weren't to send that separator as a pipe, the default separator would be a comma. So state.in. And if you look at table 5, in supports multiple arguments. That's what the third column is. Some of these operators, not only do they support multiple arguments, they have a defined number of arguments that can be passed. The first one being range, and you can think about that when you're building these queries. You're going to search where the range, and then you're going to pass it a lower and an upper, right? If you were to pass it more arguments than that, if you were to pass it more arguments than that, you would get a validation error. You would get a 400 level error that's very verbose. And I'm going to speak more about validation probably in the next slide. Returning to card 1, if you look at those query string arguments that begin with a pipe, so I'm looking at page 5, limit 30, order by, pipe fields, and separator. All of those query string arguments they're not quite operators, but if you look to the bottom right of the slide marked by 6, the header is additional query context. This is additional material that's needed to build a query, but it's not related to any specific resource. It's supported across all of the resources. Why did I use a prefix of a pipe? I wanted to try and eliminate the possibility of collisions between naturally named resource fields and what I'm getting at here for pagination, ordering, and fields. So pagination is how you would expect. When you run the application, you can set a pagination limit. If you don't, there's a default. If you don't send the page, it will call page 1. Ordering, the ordering context, if you look down on table 6, the example there is field A, descending, comma field B, comma field C, descending. Field B is ascending. You can send ASC. You don't have to, that's the default. It understands that. But that's how you would order fields. Speaking of fields, if you were to move up 1 in table 6 and look at the pipe fields record, the third record, these are the fields to return. Anytime you're reading a record, you don't have to get all the fields. Select star from table. You can specify which fields you actually want, and that's really useful. And the last is separator. Again, I noted the typo today. I will put in an issue to get that fixed. But what this does is, by default, the separator is a comma. If for whatever reason you didn't want to use a comma, you could dictate what you want the separator to be. But that will only apply to the actual fields on the resource. So in the example, back to card 1, the last query string argument is pipe separator, and we're declaring that it be a pipe. And we're using that pipe on the second argument, state.in. We're separating New Jersey and Pennsylvania with a pipe. However, that pipe is not being considered later on with the order by or fields values. Those will always be commas. Table 3 API REST endpoints. So when you're building out these REST APIs to do database operations, not only do you have to map out what the query string and the bodies are going to look like, you also have to consider what's the URL structure going to be like. So what I have in table 3 are the patterns that are used by this application. So there are 5 actions that I have listed there: create, read, update, delete, and read. That last read is a search. So and I distinguish between a single unique record read and a table search. So let's look at the first four. Create, read, update, delete. So create, that's HTTP post. A note for using this application is you can create one record or many with a call, and that's across all the interfaces. It functions the same way for GraphQL and gRPC. You can create one record or many. A word about validation. If you have a database table and you're trying to create a record on the table and there's a field that's required, which is dictated by the GDL, and you don't include it, you're going to get a 400 level error with a verbose message. If there's a field that is of numeric type and you send it a string that can't be quickly cast to an integer or a numeric type, you're going to get a 400 level error. That's the way the validation works. If you call a resource that doesn't exist, you're going to get a 400 level error. And that's the validation that happens at the source. And it doesn't just happen on the create, it happens for all of the operations. So for example, with read, the next one there, this is reading a unique record. So read, update, and delete, these are operations that happen on a single unique record. These endpoints, these resources don't get provisioned if the database resource doesn't have keys. So if you have a table with primary key, that table is going to support reading a single record, updating and deleting a single record. If you have a table without keys, or if you have a view or materialized view and it's not keyed, you can search that table, you can create to that table, but you can't update and delete and read an individual record. If it is keyed, let's just think the most simple. You create a table that has a primary key. The way you would read that is you would read that record. So now I'm looking at table 3 and I'm looking at the second record, read, get, and then the path there is service, I'm passing in a resource parameter. And the parameter is going to be what's indicated on card 1, schema underscore table view, materialized view. Anyway, back to table 3, you would make a GET request to /service/resource /record, and /record is it's literally /record. That's what the string literal is going to be, and then you're going to pass as query string arguments the keys. So if it's a composite key, you'll pass all the fields and all the values that make up that composite key. If it's a single key, you'll pass in the field name and the key, and you'll get the single record back. And that's also how update works and delete works. Now the last one's the most interesting one, the read, the 5th record there, because at all the places I've been, that's the one that's used the most. You're searching tables, trying to get pages, result sets back to calling clients. And for that's the example we went over first. That's the example marked in card 1. A couple of things I wanted to mention more about functionality and features. So all of those actions, create, read, update, delete, and search, they all support the additional query context. So you can, for fields, so you can declare which fields that you want for all of the calls. Not all of the databases support returning data on mutations. I actually mentioned that on a later slide, but think about Postgres. Postgres does, and if you update a record or you create a record, you can return the record back within the same request. So you can imagine if you posted form data, from a user, if you posted it to this endpoint, and the table that it was writing to had a date and timestamp or maybe an auto-incrementing key, you can actually return that material back within the same request-response lifecycle. The last piece worth noting here for the REST interface are the headers. So there are 3 headers that are used in this application. There are 3 headers. The first one there always comes back. I call it request ID, right? So when a request comes into the application, it gets issued a UUID. I implement COA, so that UUID gets attached to the request.state space on the object. And then for the remaining time that request is in the application, anytime there's a log statement, that UUID gets injected into the log. And that makes it very easy for troubleshooting and finding out what happened. The other headers are optional. You can send them if you want. So the first one is xGetSQL. If you chose to send that key and you send it a truthy value, what would happen is, as we went over with card 1 and card 2, the exercise is to build a REST query and generate SQL and then execute it. Well, whatever SQL gets generated, you can actually get back as text in the header. If you were to send xGetQuery with a truthy value, it would actually send you back the SQL string that was generated for you to inspect. The last one is getCount. It's xGetCount. And again, that's optional. If you were to send that and you were to send it a truthy value, you would get the unpaginated total back. So the way that would work is going back to card 1 there. If we're doing a search based on this record, maybe we're looking at users or candidates. Maybe it's an applicant tracking system. So I'm going to search for this table. I'm going to search for occupation as engineer, and the person is in New Jersey or Pennsylvania, and they have a handle of sudo. I'm getting page 5 back and 30 records per page, but I also need to know the unpaginated total so that I can render the pagination correctly. So the way I can get that is I can just, send that header at the very bottom of the slide, xGetCount. If I was to include that, I would get the unpaginated total count. So the way I have built this to work is that if you're going to execute these searches, when you reach out to get the first page, you would include that header. So you get the unpaginated count. But then for consecutive page lookups, you wouldn't include that. That saves a database lookup. That's what that saves. Okay, cool, moving on. Systems design. The pattern is to normalize the request that comes in, validate it, and build SQL. So normalize. Indicated at the top are 3 buckets. One's red, blue, and green. That's REST, GraphQL, and gRPC. We just went over in detail how the REST interface works. The others, as I said earlier, they work in similar ways. When they come in, they look different to the application. So the first thing that happens is that those unique calls get normalized. So on the right side of this slide, you'll see 3 cards now, 1, 3, and 6. 1 and 6 are the same as the 2 cards from the previous slide. 1 is 1, that's the HTTP REST GET call. And 6 here is 2 on the other, and that's the SQL that gets generated. What's new on this slide is the addition of card 3. Card 3 is a standardized object. I call it a query object. A user queried the service. This is the payload. This is the information that they sent, and here it's been standardized. So here's the way it works, working down the stack. A REST call comes in through the red bucket, looking much like card 1. It goes through the service call normalizer, which is that layer that's marked with the number 2. If the resource being called exists, it'll be normalized. If it doesn't exist, it will already respond back to the user with a 400 level error. If it does exist, it'll be normalized. That normalized object, documented by card 3, gets validated. This is where the happy validators come in. They check all the fields that are there. They check the operators that are being used. As you can see, state.in and handle.like. They're checking to make sure that the operator is supported. Some of the operators are supported by specific data types. So think about the GIS operators. So if you use a GIS operator, here it's going to check to see whether the field is of geometry type or not. It's also going to check to see if the database is postgis. So that level of validation is happening at the resource level, at the field level. It's also happening within the context. So when you're asking for fields back in ordering, it's going to make sure that the fields that you're ordering by exist on the object. It's going to make sure that the fields you're asking for exist on the object. All of that validation is happening at this layer. If it is invalid, a verbose message is sent back in the body of the response, and you get a 400 level error. If that request is valid, it continues down this chain to the query builder. That normalized object in card 3 gets passed to a function, and it builds the SQL query. That's what happens. And then the query gets executed against the database. That's actually optional. I'll mention that at the end. There is a debug mode that allows you to make a call that runs the entire length of this chain and stops just short of execution. Documentation, feature videos, and requirements. So we talked about a lot, and we've only done so in a few minutes. I want to take another moment to mention that there's 2.5 hours of YouTube video that's been up that goes over every feature and every function, all the features in the application. Some of them, most of the features are explained in REST, and then there are custom videos for GraphQL and gRPC that show you how to implement those same features in the other interfaces. If you're new to Service Engine, I would certainly recommend that you run through all of the features from the REST point of view, and then take a look at the other interfaces. Running down that list to make sure that I explain all the features. The quick start, those are that's basically what we went over in the second slide, how to run the application in a Docker container. The key REST points, I showed you a subset of those earlier. There are additional key REST endpoints, specifically like the results of the database survey. That's a key REST point. There's a video on importing an OpenAPI 3 document into Insomnia for anyone who hasn't done that. There's a video that shows you how to do that. The next feature videos on YouTube are CRUD operations. So it's the create, read, update, and delete, and showing you how to call the different URLs and how the validation works and the headers. The next one is SQL operators. So I haven't looked at that in some time, but I'm thinking it's probably a table search and showing you how to use all the various the operators that are there. API response metadata. That video goes over the 3 different headers that are supported in the application that we went over. Debug mode. This is where, so moving up a couple slides. Here, if you look at, we can look at card 1 or card 3. Card 3. So at the very end, we're doing a read. It's a GET request. This is a table search to /service/resource. If you were to change the literal /service, if you were to actually change that to /debug instead, so you were calling /debug/resource, the application would function in all the ways that I described. It would just stop short of calling the database. So the query would get built, and then you would get a verbose response back explaining what happened. This could be useful in testing. This could be useful for a number of other things, like if you were gonna use Service Engine to build sophisticated complex queries, maybe you could use it for that, but not execute them. It could be useful there too. What's next? Permissions. The database survey pulls internal tables and lists out all of your tables using materialized views. When it starts up, it provides by default CRUD access to all of the objects. There is a mechanism for passing in a configuration that allows you to set resource level controls over what create, read, update, and delete functionality you want to support on any of the resources. And that video shows you how to do that. So imagine if you wanted to set an entire, all the objects in the service to read only, but then there were a couple tables where you wanted to set as create or read. You could do that using the permissions. Database schema migrations. As I said earlier, I implement the database schema migrations that are implemented in Connects. I did build a very small custom module that works to only push the SQL files into their own directory. When I'm looking at SQL files, I like to see them as .sql as opposed to having JavaScript SQL strings inside of JavaScript files. But if you watch that video, you'll see the custom work that I put in. It's very small, but I like it. GraphQL Playground and Geoqueries, and then the next one is gRPC service and Geoqueries. Those 2 videos cover the other interfaces, and they go over all of those features from above. Complex resources, subqueries, and aggregate queries. This application, it's powered by a database survey. So the table view and materialized view being queried has to exist. Now, a subquery and an aggregate query, it doesn't exist as a resource in the database, but it is built on objects that do exist. So this application does support those kind of queries right now. You have to pass in a configuration. Basically, you have to pre-build how the aggregation is going to work, and that video shows you how to do that in detail. The last feature video there is middleware and redactions. Redactions I'll hit first because it's easier. Think maybe you want to support searching on a field, but you want to prevent it from being exposed to the user. Or maybe you just want to prevent it from being exposed to the user, not even facilitate it for search. So think about like maybe you've implemented IDs and keys and you hold those as different fields. And maybe you want to publish the ID but withhold the key. Maybe you're thinking about changing keys. Maybe it's a partition key and you want to maintain the ability to swap those keys or to re-optimize your database without being concerned that people who have had access to that record in the past are going to try and query off of that material. Middleware. Middleware is what I mentioned on the first slide, which is the ability to intercept a query before it gets executed. So if we go back up one, if we're running down this stack and a call comes in and it gets normalized and validated, between validation, but before the query gets built, the middleware is a function that will receive the object defined in CRUD3 and will be able to modify it. So the example that I can think of is partition keys. Imagine if you have users by state, and maybe you have them segmented into, I don't know, NCAA, like the SEC, what are those, conferences, right? So maybe that's it. Maybe you're building an application for NCAA and you have users and you want to be like, okay, this is the conference. So what you would do is you would take the state that they're in, or maybe the location from their IP address you would derive. You would be able to do that. You would be able to do that lookup inside of the middleware and append the conference as a key to the object defined in line 3 using middleware. So whoever's calling your API would only be calling with something very normal. What's data my end? They would have no idea that you're doing a conference lookup in the back and you're appending that to the query. Application considerations. As I said in the beginning, if you're using a database supported by Connects, generally this should work. A couple things to consider. A couple things to consider. The first is GraphQL schema definition language. So the names of your databases, schemas, tables, views, materialized views, and your fields, the names matter. This application executes a database survey and it provisions everything upon that. And one of the things it provisions are the GraphQL schema object and the GraphQL resolvers. But the schema definition language supports only a very narrow set of fields. I believe off the top of my head it is alphanumeric and underscores. That might not be all of it, but I think that's it. So if you attempt to run the application and your database uses different names or white spaces or things like that, it might not work, but you should get a message right away indicating what the issue is. The next thing is database permissions. When the application runs by default, it runs migrations. That's on when you start the application, let's go back a couple slides. We're looking at the startup sequence. When you run the application, by default, it will, on startup, it will attempt to run database schema migrations. So it will check a directory on the disk in the container, and it will attempt to run the schema migrations that it finds. Now, when you run by default, it's not going to find any. But that doesn't mean it's not going to run the migrations. And part of running the migrations for the first time or every time is checking to see if a database schema migration table exists in the store. And if it doesn't exist, it will attempt to build it. And I'm only going over that in such detail because if you were running it, imagine if your database user has access to create, read, update, and delete to and from objects, but you don't have the ability to create new objects, you're probably going to have a problem. So what you can do is there are methods for running the application and disabling database schema migrations at startup. And that's what I would recommend. And there's a video on that to the left that you can go find. Another reason why you might want to disable database schema migrations when the application starts is you might want to push your DDLs into version control and set up a CI/CD job that when merges to different branches occur, the CI/CD job pulls down the changes and executes the migration only one time, as opposed to deploying, a batch of 12 or 20 different containers in a cluster and having every single one of them start up and try to execute the same migrations. I don't think that would be a problem. It's just overhead you don't have to deal with. The last is returning fields. I did mention this earlier. Not all of the database dialects support returning fields on mutations. So what I have listed here at the end is MySQL and SQLite. They don't. So if you were thinking back to our REST example, if you were to create a record or update a record, if you were using those databases, you're going to get a 201 with a no body, a 201 status code, and you're going to get a no body. But if you're using Postgres or one of the other databases that do support returning fields, you're actually going to get the fields that you asked for back. That's pretty cool. Closing notes, last slide. Starting with the most obvious, that's me. Hello, my name's Joe Wingard. There's my contact information, my GitHub, Keybase, and LinkedIn. So if you have any notes about this talk, send me a note. I'd love to hear it. So project feedback and closing thoughts. We'll come back to that. Well, first, I want to talk about the imagery here. So on the left and the right. On the left, I have a stack of 5 different databases. I have them of several of the different database dialects supported by Connects. They don't have to be that. They could just be different databases. But here I have Postgres and MySQL, SQLite, SQL Server, and Oracle. And each one of those databases is, there is an instance or many instances, right? If you're scaling, instances of Service Engine connecting to that database, publishing REST, GraphQL, and gRPC services. And on the right side of the slide, I have diagrammed a reverse proxy or an ingress or it's a proxy that enables you to basically virtualize your data access layer. So at api.domain.com, at that subdomain, you would be able to make any of the calls using any of the interfaces to any of the resources across any of the database engines. And whoever's calling, your other engineers who are calling your data access layer, would not have to really be concerned with what the database, they wouldn't even know what the database is, possibly. And here, this is how I would recommend deploying your data access layer. There's many reasons why I'm happy to get into. If you send me a note, we can have a discussion about it. But you get a lot of wins by deploying a system in this manner. Project feedback. Feedback and recommendations are best received with pull requests and GitHub issues. The feedback I care about hearing the most is from people who like to roll up their sleeves and dive in. So if you're one of those people and you have some feedback, open up a pull request or a GitHub issue and let me know what we can do to make this better. And the closing thought, I hope this project is useful to you and your team. If you find it valuable and helps you in your world, please send me a note. And that's it. So this is Service Engine. I just gave you an overview of. This is an NPM package. It's my first NPM package, NPM I Service Engine. And it's available as a Docker container. And there's plenty of documentation. I think you can use it right now today. So that's all. Thanks a lot for your time and cheers.